So we've already got a couple of methods up our sleeve for graphing polynomial functions. We know that we can use a table of signs if we need to help us find the shape of a curve on either side of its zeros. So if you're looking at a curve and you're just identifying the zeros by saying let's let p of x equal 0, then one of these parts must have been 0, then we can see that we've got zeros at 0, -2, and 1. So putting them onto a table of signs in order from smallest to biggest and leaving a gap on either side of them, we get something like this. Now it's tempting to put actual numbers in here and then work out the numbers of all of these. We know that these are zeros, so we can put those in easily. But a quick tip to save a bit of time: if you actually put -3 in here and then go and figure all of this out, you'll end up doing a lot in your head or perhaps needing to do a lot of working. -3, so that part's 3, and here I've got -3 plus 2, so that's -1, and squared, that's 1, and then here I've got -3, -1, so that's -4, and now I need to multiply these together to get -12. Now there's nothing wrong with doing that, but a lot quicker to just look for the sign, because all we're really interested in is whether it's positive or negative. So if I think -3, but don't write it, you can leave that blank, but actually think -3, well that's positive. -3 plus 2, anything squared, this is going to be positive, this part. And -3 minus 1, this is negative. Multiplying positive by negative is going to give me a negative, and that's much quicker and easier for me to do. So, filling in the rest of this, when x is, say, -1, I'm going to have -1. This part's going to be positive, and this part's also going to be negative. I'm going to get the same thing. When x is, say, 1/2, I'll have -1/2, so this will be negative. This part's always positive because it's squared, and 1/2 minus 1 is negative. So negative times a negative times another positive will be a positive, and when x is, say, 2, this would be negative. This is always positive, and this part would be positive. So I've got a negative times 2 positives, and that's a negative. So now I can use that information to say, well, what's happening on either side of this x equals 2 spot? It's negative on both sides. So there's only one way I can do that: it must just touch. Whereas on either side of this zero, it goes from negative to positive, so it must come through here like this somehow. And on either side of this one, it goes from positive back to negative again, so it must turn around and go down. That's a perfectly okay way to do it. But it's usually a lot quicker to use our understanding of the degree. Now, what's the degree of this thing? Well, it's got an x here. This part would expand out to give us an x squared, and here's another x. So altogether, this has got a degree of 4. So it's a quartic curve, isn't it? What do they look like? Well, it can be sort of a fat-bottomed parabola, or it can be a wobbly sort of W shape. We can also then use the sign of the polynomial. So it's a -1, and that tells me that it's something of this sort of nature, perhaps. And then lastly, and this is the one to give it away, we use the multiplicity of the zeros. Now, we've talked about multiplicity before, we just haven't actually used this name to describe it. And what it refers to is the fact that you can have single roots, like these two, double roots, even triple roots, quartic roots, etc., and they behave a certain way. Now, we've learned that a double root has this nature where it just touches the x-axis and then glances off. But if we're using those three things together, then we should be able to complete this graph without needing the table of signs at all, because we're thinking about this shape. So as we put a spot here for each of our intercepts that we can read off our polynomial, we can see that this one is a double root. So we know that we're starting low, so we're down here, and this one's going to be a double root which behaves like this, whereas these other two are single roots, which means we need to actually pass through the x-axis and then pass through it again. And that is a much quicker way to make our graph. So a simple table here to explain multiplicity of zeros, we can have a single or a simple one, which just has a multiplicity of 1. And an example here would say that both of these zeros at x equals 1 and x equals -2 are simple or single ones. A double zero has a multiplicity of 2, and we see that that's when we get one of our zeros actually squared. So in this example, that's the part that has a multiplicity of 2. This part only has that multiplicity of 1. And then a triple zero has multiplicity 3, and that means that that 0 has been raised to the power of 3. So in this example, it's this part. Now simple or single zeros just cross the x-axis by going across it. So that means that their gradient can't be 0. They're not horizontal at that point. They're either going up or they're going down, and they're crossing it. Whereas if the multiplicity of a 0 is even, then we get a turning point at that 0, and the curve does not actually cross the x-axis there. And we've seen that it looks like a section that just touches from above or from below. Whereas if the multiplicity of a 0 is odd, then we get what's called a horizontal point of inflection. Now we haven't looked at these a lot yet, but we have seen them when we graphed the curve y equals x cubed, which has that shape. It comes up like this and then has a little flat spot there before going up again on the other side. Now that flat spot there is a little section where the gradient is 0. So this explanation here is actually quite different from both of these, because in both of these situations, just as it crosses or just as it meets that 0, it is in fact a little flat spot. And this one isn't. So let's have a go now at drawing each of these just using the multiplicity. This one's just a basic parabola. It's got a degree of 2. So that's very easy to draw. It's got a 0 at 1 and another one at -2, and it's an upright one. So I know it's going to look something like this. Good enough. I could put the y-intercept in there if I want to and say that's -2. The next one, it's got a double 0 at x equals 1 and a single one over at -2. So it's a cubic curve and it's an upright one, or a positive one, so that means that it's going to come through this intercept at a gradient that's not 0. But this one, it's going to just touch like that, and that's what we call a turning point. Graphing the last one, I can do that down here. Can you still see that? No, let's do it up here. We've got the same two intercepts at 1 and at -2, but this one is a triple, and so it looks like that horizontal point of inflection. Now, what type of curve have we got here? It's a quartic one, isn't it? Which means that we're looking for something of that W sort of shape. That means it starts high from over here. So as it goes through this point, it's going to have to come down and then flatten out before then passing through it. Now, it only is able to pass through this one more time, so it must at some point down here turn around and go straight up through that one. So it sort of has a bit of a funny sort of wobble to it, this horizontal point of inflection. We'll see them a lot more in this course, but at this stage, that's enough for you to be able to graph all 3 types. And we can see that our rules here are applying to oddness or evenness. So that allows us to actually graph zeros that have any multiplicity that we like.